Dear students, in this lecture video we are going to solve a problem on weighted residual technique. So this is the problem statement. The following differential equation is available for a physical phenomenon. D square y by dx square minus 10x square is equal to 5 within the limits 0 to 1. Okay. The boundary conditions are given in the problem as y of 0 is equal to 0 and y of 1 is equal to 1. By using Galerkin's method of weighted residuals, find an approximate solution of the above differential equation and also compare with the exact solution. Okay, so this is the problem statement. The given governing differential equation is d square y divided by dx square minus 10x square is equal to 5. Okay, between the limits 0 to 1. We can keep this as equation 1. In the problem, we are asked to find the solution for this differential equation. Okay. The boundary conditions given in the problem are the first condition is y of 0 is equal to 0 and the second condition is y of 1 is equal to 1. To solve this problem using Galerkin's method of weighted residuals, we are in need of assuming a trial function. Here, for simplicity, we can choose a polynomial function of order 2 as the trial function. Y of x is equal to a naught plus a1x plus a2x square, because the given differential equation is of order 2, so that we have to assume the trial function with order 2. Okay, we can keep this as equation 2, but we have to select the trial function which should satisfy the given boundary conditions of the problem. So we can make this assumed trial function which will be satisfying the given boundary conditions by substituting the given boundary conditions. Okay, so first, by applying the first boundary condition, in equation 2, that is y of 0 is equal to 0. That is, at x is equal to 0, the function y will be equal to 0. Okay, so equation 2 becomes a naught plus a1 into 0 plus a2 into 0 square is equal to 0. By substituting the value of x as 0 in this equation 2, the value of y will be 0. That is the first boundary condition. On applying the first boundary condition, we will be arriving at the result a naught is equal to 0. Next, we can apply the second boundary condition. In equation 2, that is y of 1 is equal to 1. A naught plus a1 into, for x, we have to substitute 1 plus a2 into 1 square, which will be equal to 1. That is the second boundary condition. In the previous step, on applying the first boundary condition, we have found out the value of a naught as 0. So a1 plus a2 is equal to 1, from which we can arrive at the relationship between a1 and a2 as a1 is equal to 1 minus a2. Now we can substitute the found out values of a naught and a1 in equation 2. Y of x will be a naught is 0 plus a1 is 1 minus a2 into x plus a2x square. The assumed general trial function is a naught plus a1x plus a2x square. We have substituted the value of a naught as 0 and a1 as 1 minus a2. This can be expanded as 1 into x is x minus a2x plus a2x square In the second and third term, a2 is a common term. So by taking a2 as a common term in the second and third terms, x square minus x plus the first term plus x. Okay, this is the feasible trial function we can assume to solve a given problem which will satisfy the given boundary conditions of the problem. Okay, now we can proceed this problem to find out the solution with this trial function. Okay, in the next step of the problem, we need to find out the residual function. So here in equation 3, we have a function y of variable x. Okay, in the first equation, we have the governing differential equation of order 2. So by comparing the equations 1 and 3, we can calculate the residual function. So to compare these two equations, we need to differentiate equation 3 twice with respect to x. Then only we can have an expression with d square y by dx square. Then only we can compare the double time differentiated expression of 3 with the equation 1. So on differentiating expression 3 with respect to x, dy by dx will be a2 into the differential form for x square is 2x minus for x 1. Okay, plus the differential form for x with respect to x is 1. d square y by dx square will be a2 into the differential form for 2x is 2 minus the differential form for 1 is 0. Again for this one also the differential form is 0. Okay, so this can be simplified as 2 into a2. Okay, so here we have the expression as d square y by dx square is equal to 2a2. In the governing differential equation, we have d square y by dx square minus 10x square is equal to 5. Now we can replace this d square y by dx square by this 2a2. Okay, because we have found out the d square y by dx square value from the assumed trial function as 2a2. So now by comparing this expression with the expression present in equation 1, by replacing d square y by dx square term in equation 1 by 2a2, the remaining terms in equation 1 are minus 10x square minus 5. Okay, this is the residual. Okay, so the residual function R for the present problem for the assumed trial function is 2a2 minus 10x square minus 5. Now we can use the Galerkin's weighted residual approach. The general form of the Galerkin's weighted residual approach is integral 0 to L Wi into R dx is equal to 0. Okay, so here Wi is the weight function. So weight function is nothing but the coefficient of the unknown constant term present in the trial function. Okay, so here our trial function is y of x is equal to a2 into x square minus x plus x. Here the coefficient of the unknown constant term a2 is x square minus x. So in the present problem, the weight function wi is x square minus x. Okay, and the residual function we have found out in the previous step of the problem. The limits are given in the problem as 0 to 1. So by substituting all the known values, the Galerkin's form will be integral 0 to 1 weight function x square minus x into residual 2a2 minus 10x square minus 5 into dx is equal to 0. So by multiplying these two terms x square minus x and the residual function integral 0 to 1, first we can multiply this x square with this residual function. So x square into 2a2 x square minus x square into 10x square, 10 into x power 4, then x square minus 5 minus 5x square. Okay. Next we can multiply this minus x with the residual function. Minus x into 2a2 minus 2a2x minus x into minus 10x square plus 10x cube minus x into minus 5 plus 5x into dx is equal to 0. Okay. Now we can integrate the available function 2a2 x square. The integral form is 2a2 into x cube by 3 minus 10 into x power 5 by 5. The integral form for 5x square is 5x cube by 3 minus 2a2 x square by 2 plus 10 x power 4 by 4 plus 5x square by 2. This is the integral form. The limits are 0 to 1 is equal to 0. Okay, here we can cancel these terms 2 and 2, and here 2, 5. In the next step, we can substitute the limits. First, by substitute the upper limit in the function, that is x is equal to 1. So 2a2 by 3 into 1 cube minus, here also we can cancel this 10. So this will be 2 into 1 power 5 minus 5 by 3 into 1 cube minus a2 into 1 square plus 5 by 2 into 1 power 4 plus 5 by 2 into 1 square. Okay, minus, by substituting the lower limit 0, all the values becomes 0. So this will be equal to 0. So the above expression can be simplified as 2 by 3 a2 minus 2 minus 5 by 3 minus a2 plus 5 by 2 plus 5 by 2 is equal to 0. Now we can group the coefficient terms of the unknown a2. So here 2 by 3 a2, so the coefficient is 2 by 3. Here minus a2, so the coefficient is 1. We can take the constant terms in the right hand side of the expression. So 2 plus 5 by 3 minus 5 by 2 minus 5 by 2. This can be simplified as minus 1 by 3 a2 is equal to 12 plus 10 minus 15 divided by 6, that is minus 8 by 6. Okay, minus 1 by 3 a2 is equal to minus 8 by 6, from which we can calculate the value of a2 as 4. Okay, now we can substitute this a2 value in the trial function present in equation 3. Y of x is equal to a2 into x square minus x plus x. This is the solution of the given differential equation. In the problem, it is asked to compare this weighted residual solution with the exact solution. So we can calculate the exact solution for the given differential equation. The given differential equation is d square y by dx square minus 10x square is equal to 5. So d square y by dx square can be written as 10x square plus 5. We can integrate both the sides. So on integrating once, in the left hand side, the term will be dy by dx. The integral form for 10x square is 10x cube by 3 plus 5x plus a constant of integration c1 gets erased. Once again, by integrating, here this term will be y 10 by 3 into x power 4 by 4 plus the differential form for 5x is 5x square by 2 plus c1 into x plus again in this step also a constant of integration will get arise. So y of x is equal to 2, 5. So 5x power 4 by 6 plus 5x square by 2 plus C1x plus C2. We can keep this as equation 4 and this as equation 5. Okay. We can calculate the values of C1 and C2 by applying the given boundary conditions. Okay. The first boundary condition is y of 0 equal to 0. By applying this boundary condition in equation 5, y of 0 is 5 by 6 into 0 power 4 plus 5 by 2 into 0 square plus C1 into 0 plus C2 is equal to 0. That gives the value of C2 as 0. Okay. On applying the second boundary condition, that is y of 1 is equal to 1, in equation 5, y of 1 is 5 by 6 into 1 power 4 plus 5 by 2 into 1 square plus C1 into 1 plus C2 value we have calculated in the previous step as 0 is equal to 1. Okay. On resolving, we can get the value of C1 as minus 7 by 3. Okay. Now we can substitute the found out values of C1 and C2 in equation 5. The exact solution for the given problem is y of x is equal to 5x power 4 by 6 plus 5x square by 2 minus 7 by 3x. Okay, we can keep this as equation 6. In the problem, it is asked to compare the weighted residual solution with the exact solution. For that, we can assume three values between the limit 0 and 1, 0.25, 0.5 and 0.75. For these three values, we can now compare the solutions. Galerkin solution, exact solution, difference. Okay. In equation 4, we have the solution obtained by applying the Galerkin's weighted residual approach. In equation 6, we have the exact solution of the given differential equation. So first, by substituting the value of x as 0.25 in equation 4, we can obtain the result as minus 0.5 for y. Okay. By substituting the value of x as 0.25 in the exact solution present in equation 6, we can obtain the result as minus 0.4238. So the difference between the results is only 0.0762. Okay. Next, considering the value of x as 0.5, the Galerkin solution is minus 0.5 and the exact solution is minus 0.4896. The difference between these two results will be only 0.0104. Okay. Next, for the value of x as 0.75, the Galerkin's result is 0 and the exact solution is minus 0.0801. The deviation between these two results is only 0.0801. That's all about the problem.